Hello and welcome. In this video, we're going to talk about what a differential equation is and how to solve a differential equation analytically using the separation of variables method. We're going to talk about the difference between a general solution, where we still have a constant of integration, and we're going to talk about a particular solution where we're given the specific or the particular curve that is the solution to that differential equation through a particular point. So let's go ahead and jump in. So first things first, what is a differential equation? A differential equation is just an equation that contains a derivative. So for example, dy dx equals x to the third has a derivative because it says dy dx. This example down here in the box has a y prime in the equation. So that would be a differential equation, an equation that contains a derivative. There are a lot of different types of differential equations, but in this course, the only type we're going to talk about actually solving are equations where we can separate the variables, meaning we can actually get all of the things related to x on one side and all of the things related to y on the other side, which actually allows us to solve the differential equation. And if you think about what that means, we're starting with an equation dy dx, and our ultimate goal when we're solving it is to get a function y equals something. And how do we get rid of dy or dx or both? How do we get rid of a derivative? We integrate. So that's going to be the idea that we're keeping in mind here. I want to solve this differential equation so I can get back to a solution that is a function. And when we integrate, if we don't have any initial conditions, we end up with a plus c, a constant of integration. And that's called a general solution, where we still have a plus c value. Anytime you're solving a differential equation, you're going to get the general solution first with a plus c value. And that would be the solution of that entire family of differential equations. Every possible solution, that's why we have c holding the place of any possible value. But then if we're given an initial condition, or if we're given any one point, then we could take that one point and we could find a particular solution, which gives us a specific curve, or it gives us an exact function with no more plus c. So let's look at some examples and work through these together. The very first thing that we're going to do anytime we're solving a differential equation is we're going to make sure that it has a dy and a dx instead of using y prime. So here on this example to the right, it says x plus 2y times y prime equals 0. We're just going to go ahead and rewrite that as x plus 2y dy dx equals 0. And if you want to be really fancy, you could say let y prime equal dy dx. But for right now, we're really just trying to get an understanding of what we're doing here. The second step says that we want to separate like variables. So I want to get all of the x's on one side and all of the y's on the other. So I'm going to subtract x on both sides. So 2y dy dx equals negative x. And I still see that I have dx on the left-hand side of this equation. And if I think about dy dx like a fraction, what dx is doing on the left-hand side is it's dividing. So I can multiply on both sides. I can multiply both sides by dx so that I have dy and y on the left-hand side of this equation and x and dx on the right-hand side of this equation. Now here's why. To get rid of a dy or to get rid of a dx, what we need to do is we need to integrate both sides. And since I have separated my dy and dx, I can integrate the left side that has all the y stuff with respect to y. And I can integrate the the right side, which has all the x stuff. I can integrate that with respect to x because the right side says dx and the left side says dy. So if I integrate this, on the left side, I'm going to get y squared. And on the right side, I'm going to get negative 1/2 x squared, or negative x squared plus negative x squared over 2 plus c. Now you don't need a plus c on both sides of the equation because c is just holding the place of some arbitrary number, some constant of integration. So as long as you have a c somewhere, you're covering the fact that there could be some other number somewhere in this equation. Now, oftentimes you can stop here, but since we want our final answer to be a function, we're going to solve for y here, which means we're going to square root both sides. If we square root both sides, we need to consider both the positive version of what happens when we do that, and we need to consider the negative version of what happens when we do that. I do want you to separate these out as two separate functions because sometimes when you have something written as plus or minus the square root, it looks like you're including both. We're talking about a function here, so it will never be both the positive and the negative version. It will always either be something plugged into this function on the left or something plugged into this function on the right. So that's the basic process. If we were given an initial condition, then we could plug that ordered pair x, y in, and we could solve for our c value, and we could rewrite a particular solution as something that no longer has a plus c. But let's go ahead and look at some more examples. So again, our goal here is to make sure we have dy dx, get all of the pieces that contain y on the left and all of the pieces that contain x on the right, integrate both sides, and then solve for y. Let's look at another example. Okay, so here on example A, we are given this differential equation dy dx equals x times e to the x squared over y. So the very first thing that we want to do, it's already written as dy dx. So now we want to get all the y's on one side and all the x's on the other side. So dy, if I want to move y to the other side, I need to multiply it. So y times dy, and if I want to move dx to the other side, I need to multiply it, equals x e to the x squared dx. So I have separated my variables, y on the left, x on the right. Then we're going to integrate both sides with respect to the dy or dx that's on that side. If I integrate y, I get y squared over 2. If I integrate over here on the left-hand side, I'm going to need to use U-Substitution. So I'm going to let u equal x squared, so du equals 2x dx, which means that dx is du over 2. So we're going to integrate x times e to the power of u times du over 2x, and the x's divide out. So we're going to have y squared over 2. I'm going to take this 2 that's in the denominator, I'm going to move it in front of the integral. So 1/2 times the integral of e to the power of u du. And what's the integral of e to the power of u du? That's going to be 1/2 times e to the power of u plus c. And then I'm going to go ahead and put back in what u was, e to the power of x squared plus c. Now, in order to solve for y here, we need to multiply both sides by 2. So if I multiply everything on both sides by 2, that's going to give me y squared equals e to the x squared plus 2 times c. Because remember, every single piece needs to be multiplied by 2. And remember that c just represents some number, so it seems kind of silly to just say 2 times c. What we can actually do, and you could write it as 2 times c if you want to, but we can actually just change the subscript on our c, because if I multiply c by 2, it's still just some number, and that's what c stands for. It stands for some number. But I need to have some sort of subscript here to indicate that from this first line in black to this next line, I have changed this value of c. So I'm going to add a subscript, but you could really just think of that as that green c sub 1 is really 2 times c. And if you prefer to write it that way, you can. Now I need to square root both sides to solve for y. So y is either going to equal the square root of e to the x squared plus c1, or y is going to equal the opposite of the square root of e to the x squared plus c1. So this is our general solution because it still has a plus c here. What part B is going to say is go ahead and find the particular solution. Find the solution to this differential equation if we know that it has to pass through the point 0, 3. Sorry, 0, negative 3. Now, looking at these two different equations, only one of them will give you an output that's negative, right? And if you notice the y up here, this y is negative. So I need to use y equals negative square root of e to the x squared plus c1. Otherwise, it would not be possible for y to be equal to negative 3 like it says in this point. So I'm going to plug in negative 3 for y and 0 for x. E to the power of 0 is 1. So I'm going to get 1 plus c sub 1. I'm going to divide that negative out, so these can both just be positive. And then I'm going to square both sides to get rid of the square root. So 9 equals 1 plus c1, which means that c1 is 8. And then I'm going to rewrite it to get my particular solution. I'm going to rewrite the equation that I found in part A, except I'm going to plug in 8 for c1. So y equals negative the square root of e to the x squared plus 8. So this particular solution is the solution to this differential equation that passes through the point 0, negative 3. These two general solutions are the solutions for every possible differential equation that started with this. The solution to every differential equation up here is one of these two things, falls into one of these two functions. All right, we're going to work through a few more examples together. Okay, so find the general solution, and then if you're given enough information, find the particular solution. So we already have dy dx here on number 1, so I'm going to go ahead and separate the variables. I like my dy to be on the left, so dy is equal to x to the third dx if I just multiply both sides by dx. Then I'm going to integrate both sides with respect to the dy or dx on their side. The integral of dy is just y. You can think about this as 1 dy. If I integrate 1, I get y. On the right-hand side, I'm going to get x to the 4th over 4 plus c. And this is already solved for y, so this is my general solution. If I'm given an initial condition, so we're given the ordered pair 1, 1/2, y of 1 equals 1/2 means that we have the point 1, 1/2. We can find c for this particular solution. So 1/2 equals 1 to the 4th is just 1 over 4 plus c. So here is c is going to be 1/4, so I can find the particular solution. Y equals x over 4 plus 1/4. All right, let's go ahead and look at number 2. On number 2, I'm going to let y prime equal dy dx. So dy dx equals sine of 2x. And I'm going to go ahead and separate the variables. Dy equals sine of 2x dx. Then we're going to integrate both sides. The integral of dy is going to give us y. On the right-hand side, if you need to use U-substitution, you can let u equal 2x. So du is 2 dx. So dx is equal to du over 2. If you can see how to reverse the chain rule on that integral without using U-substitution, that's great. Go ahead and go about it that way. So this is going to become the integral of sine of u times du over 2. So that's going to give us y equals, well, what do I, first of all, actually, I'm going to take that 1/2 out in front. What is sine of u the derivative of? Sine of u is the derivative of negative cosine. So I'm going to go ahead and put a negative with my 1/2 and say cosine of u plus c. So our final general solution is going to be y equals negative 1/2 cosine of 2x plus c. This problem didn't give us an ordered pair to find a particular solution, so all we are going to be doing here is finding the general solution. So every solution to this differential equation is of this form, y equals -1/2 cosine of 2x plus c. All right, 2 more examples. All right, you knew it was coming. I'm going to ask you to pause the video and try and work through these 2 examples on your own. And I'm actually just going to ask you, don't worry about finding the particular solution just yet. Go ahead and just try to find the general solution. And then unpause the video and see how you did. Okay, so hopefully you've had time to give this a try. The first thing we're going to do on number 3 is separate those variables. So dy is going to equal x to the third minus 4x dx. Then we're going to integrate both sides. So y is going to equal x to the 4th over 4 minus 4x squared over 2 plus c. Or y is going to equal x to the 4th over 4 minus 2x squared plus c. For number 4, I'm going to rewrite dy dx equals, and I'm actually going to split this into 2 fractions, only because I know that when I get to integration on both sides, it's going to make my life much easier to not have this sort of quotient rule looking function, to have this division. It's going to make my life easier to not have that. So I'm going to multiply both sides by dx. X over x is 1, so 1 plus 2 over x dx. Now I'm going to integrate both sides. dy, the integral of dy is y. If I integrate 1, I get x. If I integrate 2 over x, I get 2 times natural log of the absolute value of x plus c. So both of these are my general solutions for these 2 problems. Now, I encourage you, if you have not already tried, to go ahead and pause the video and try and find the particular solution, and then unpause the video and see how you did. Okay, on number 3, we're going to use the point 2,9 to find the particular solution. So if I plug in 2 for x and 9 for y, I'm going to get 9 equals 2 to the 4th over 4 minus 2 times 2 squared plus c. So 9 is going to equal 4 minus 8 plus c. So c is going to equal 13. So I can rewrite this, y equals x to the 4th over 4 minus 2x squared plus 13. This will be my particular solution that passes through the point 2,9. All right, and last but not least, number 4, e squared is going to equal e squared plus 2 natural log of e squared plus c. And I can drop those absolute value because e squared is going to be positive. I can subtract e squared on both sides, so I'm going to get 0 equals. The other thing I'm going to do is I'm going to drop this 2 down in front. So this is an exponent. I can move the exponents to the front by properties of log. So this is 4 natural log of e plus c. And what's natural log of e? E to what power is e? That's going to be 1. So this is going to be 0 equals 4 plus c. So c is going to equal -4. So I can rewrite this, y equals x plus 2 ln absolute value of x minus 4. This is the particular solution with the indicated initial condition. So the solution to this differential equation that passes through this point is here. Every solution to this differential equation is this green part, the general solution. So let's go ahead and recap what we covered in this video. First, we talked about what a differential equation is, and an equation that involves a derivative. And then we talked about how to solve them analytically, separating our variables, getting our dy and dx on separate sides, integrating both sides to find the general solution, and then plugging in an ordered pair or an initial condition to find the c value if we want a particular solution. What we're going to do in the next video is we're going to start talking about what happens if we can't separate the variables. Is there a way for us to get an idea of what the solution of a differential equation is, even if we can't solve it using what we currently know? And that's going to lead us to the idea of a slope field. So go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.